Okay, grade 12s. So, um, we've been looking at doing free body diagrams and the free body diagram method of solving problems. Well, now we're going to look at a new kind of problem that we didn't do in grade 11. Okay, so add that to the list. We're going to do circular motion. Okay, now I made a note here. This note, you haven't taken calculus yet, like in sometimes when I teach this in semester 2 in a normal year, okay, not a COVID year, but in a normal year, um, the students will have learned some calculus and this will make sense to them. So I'm not going to try to make sense of the derivation of the formula. Suffice to say that when Isaac Newton came up with the formula, he developed it using the calculus that he had invented. Okay. Now I just want to talk to you about things that move in a circle. We call it centripetal motion, and the word centripetal stands for center seeking. Okay, center seeking. I'm going to explain why we call circular motion center seeking in a moment. When something's moving in a circle, and here we have something, I'm just going to go use a rainbow color and just go over this with my pen. Here's something going around, right, in a circle like this, okay? So you get the idea. It's going around like that. And the idea when you move in a circle is that at any given moment, let's say we take a snapshot of the object, okay? And we take the snapshot of the object when it's right here at the top of the circle. At that instant, it's actually moving this way, okay? So it's moving to the right at that instant. Now, at any point in the circle, it's moving in a direction like this. See, depending on where we are, at 6 o'clock down here, it'd be moving that way, right? At 9 o'clock, it would be moving that way. Now, what's happening is, depending on where our object is, as it makes its way around the circle, its direction of its velocity is changing all the time. So it's turning, right? Now, the thing about the velocity is, and I'll just put a little note here, the velocity is tangent to the circular arc, okay? So it's tangent to the circular arc. And here's the center of the circle in here. Now, if you're wondering why I constructed this picture, I wanted to compute, we're going to find the acceleration of the object. Let's pretend this object is moving at a constant speed as it goes around the circle here at a constant speed. So the speed's not changing. The only thing that's changing is the direction, okay? So if something's not changing speed, but just changing direction, is it still accelerating? And the answer to that question is yes. So if we were to find what the acceleration is, we would go through this process. So check it out. If I draw my two velocity vectors from the above picture, and I construct them tail to tail, this is how you would do vector subtraction. You would use what's called the tail to tail method, okay? And you'd find that delta V is this vector here. Now remember, to find acceleration, it's delta V over t, right? Now this is a displacement diagram here, okay? And these are similar triangles for reasons that I don't care to explain right now. But anyway, there's a displacement diagram. So in other words, the object has traveled here at the top, going around the circle. As it goes around, okay, if it travels from the top at like 12 o'clock noon there and travels over to here, this is its displacement, which I call delta R. Okay, it's just a straight line joining its beginning point and end point. And what happens is you get similar triangles, so the ratio of the sides is the same. This is calculus, which I don't want to get into because I obviously I can't teach you that, but if you had learned it already, it would make more sense. Okay, the point is right here at the bottom. So let's cut to the chase. I call this radial acceleration. Okay, when an object is moving around in a circle, now I'm going to appeal to your feelings. Okay, I'm going to appeal to your feelings. You've driven in cars and turned corners before. Now, whenever you accelerate, you feel it. You feel the sort of sense of inertia. So when you turn a corner, you definitely feel something odd there. Your body's inertia will tell you. You'll feel like you're sort of being pulled to the outside of the circle. That's always true when you accelerate. If you accelerate forward, you feel like you're accelerating back. Your body feels like it's being thrown back. If you accelerate backwards, you feel like your body's being thrown forwards. Well, if you turn to the left, your body feels like it's being pulled to the right. Okay, it's always, your inertia always makes you feel the opposite of what's actually happening in your accelerated point of view. Okay. Anyway, my point is this: the faster you make the turn, the more that you'll experience that feeling. So I think if you really turned fast, like you're driving your car and you pull a turn too fast, you will really feel that pull. If you take it really slow, you don't feel it so much. So we know that this feeling of acceleration is connected to your speed. Okay. Also, what affects you is your turn radius. Okay. Or the radius of the path that the object is taking. Okay. So the sharper the turn, the more you'll feel that acceleration, right? Now, it turns out this formula in the box here tells you really how it works. That the acceleration you experience just because you're turning, you're not speeding up, you're not slowing down, but just because you're turning is equal to v squared over r. Okay, so that's called turning acceleration. I call it radial acceleration. Okay, now the direction of this acceleration, I highlight it for you here, must be towards the center for reasons that I can't really explain unless you get the calculus, but it must be towards the center. Let me erase that. No, unless the speed is changing. It says, I'll explain that later. If the speed changes, you get two accelerations then. So the net acceleration will be towards the center. But the deal is, if you're turning, this radial acceleration is always toward the center of circle. And that's why I call it radial, because if you draw a line here, if we go back up to our circle, let's say the object's at 12 o'clock. Let me erase all some of this nonsense here. If the object's at 12 o'clock, well, the center of the circle is directly below it. I'll use a rainbow for the center. Here's the center. The object will actually be accelerating towards the center here. But then when it's in this position over here, that direction will change, but it's still towards the center. No matter where the object goes, it will accelerate in a radial sense towards the center of the circle. So one way for me to say it's towards the center, like sure, that direction is changing depending on where you are in the circle, but it's always towards the center. So I call it radial, along a radial line. Like this is a radial line towards the center of the circle, okay? All right, so we call this radial acceleration, okay? It's radial acceleration. Oops, gosh, that was horrible. Let me fix that. Oh, is it giving up on me? Okay, radial acceleration. There you go. So what have we learned here so far? Not much, okay? Whenever you're moving in a circle, you have a component of acceleration towards the center of the circle that's equal to v squared over r. So it's this formula here, okay? And the direction of that acceleration is toward the center. So I call it radial acceleration. So we're going to call it AR, A with a subscript R, standing for radial acceleration. Okay, now I summarized some notes for you down here. So radial acceleration is towards the center, okay? R is the radius of the motion in meters. V is the speed in meters per second. There's our magic formula for the radial acceleration, okay? And I've got some steps for you to solving these. These are just general sort of tips, okay? Number one, you've got to do what we always do, which is you use the free body diagram method. And of course, you solve using components. And that's broken record. We're going to do that all the time in any problem that comes up, including a circular motion problem. Now, your choice of components is critical here. I'm going to put a star by this one. We must choose, if it's moving in a circle, radial and tangential components. Now, radial is towards the center of the circle, so let me draw a circle for you. Actually, let me try this. Yay, look at that. There's a circle. Whoop, that's not a circle. It's terrible. There, that's a good circle. Okay, so here's the deal. On my keyboard. All right, here's the center of this circle here. Okay, so let's say we have an object that is moving around this circle. Well, as it moves this way, that's its velocity, okay? As it's in this spot, it's going to have acceleration towards the center, that's radial acceleration, but perpendicular to that radial acceleration is the tangential component. So I'll use a red line. This is my radial component, and I'll use a blue line. This would be my tangential component, okay, for my forces and my accelerations. Now, by the way, if you're speeding up as you're going along through the circle here, you could also have tangential acceleration, okay? So there can be two accelerations in the problem. All right, now, here's our tips. We'll continue on. You're going to use v squared over r for radial acceleration. So we're going to substitute v squared over r, where v is the speed and r is the radius. And to get the speed, well, if something's going around the circle at a constant speed, if we just go circumference of the circle divided by time for one lap, okay, that will equal the speed. So this is a very useful way of finding speed, okay, if they give you the time for one lap. All right, so let's see if we can do some examples of what to do with this. And I'm just going to do a couple of examples. There are several more that we're going to be talking about, but like for today, we'll keep it short with just a couple of examples. Now, hopefully this works. Let's see if that works. Okay, vertical pendulum. A vertical pendulum is just like, let's say I'm trying to hypnotize you. I hold a dice, or not a dice. I'm holding like some type of object and I'm swinging it in front of your eyes. If you're swinging on a swing, okay, you're on a vertical pendulum, okay? So your circular arc is in a vertical plane, okay? And here the pendulum is only completing part of the arc, and they use capital T to represent the tension in the rope, which is a changing number, but the weight of the mass is not changing, it's just mg, okay? Now, how do you work out questions involving vertical pendulum? Well, let's do an example, okay? And I'll show you, well, this will be our first example of circular motion. I'll show you how you can do a problem with vertical pendulum. So here, let's do an example. Whoop, let's go back to black. Okay, here's an example. Let's say, okay, let's say we have someone swinging here. I'll put a little guy here like this. And here he is. He's swinging on a rope. Okay, and let's give him a mass of 50 kilos, okay? Now, when he's in this position, he's moving at 3 meters per second. And what's happening is he's swinging in a vertical arc. This is what we mean by vertical pendulum, right? Let's make this angle here 30 degrees. So he's currently at 30 degrees, and he is moving tangentially with a speed equals 3 meters per second, okay? Now, the radius here, let's make the rope, let's make it like 3 meters long. So it's a 3 meter rope. Okay, a lot of threes, 3, 30, and 3, it's just coincidence. Here, if you don't like too many threes here, let's change it. Let's make the rope. I'm sorry, my pencil's sort of acting up there. Let's make the rope 2 meters. Okay, it really doesn't matter. It could be 2.5, it could be 3, it could be anything. I'm just making these numbers up, so ignore any coincidences in these numbers. They're totally unrelated. Okay, So you've got these parameters here. Now I want you to tell me, I want you to answer a couple of questions about this. What is the tension in the rope? So let me use a red vector here. We know the tension that ropes only pull on you, can only pull on you. So what is that tension, okay, when he's in this particular position? Well, let's go with that one. And also, I'm going to ask you for both the radial and the tangential acceleration. So what is the tension? That's one question. What is AR? That's another question. What is AT, the tangential acceleration? How about that? That is a kind of a brand new kind of question, right? But how we solve it is exactly the same as how we always solve questions of this type, okay? So what you do is you draw a free body diagram of the person. I mean, it's the only thing you can draw a diagram of here. So what's acting on the person? This is the easy part. One, there's gravity. Two, there's tension. And that angle of 30 degrees is going to show up right there. Okay? Actually, I don't want to put it there. Actually, hang on. Let me get rid of that for a moment. I don't want to put that in yet. What I want to do is just extend this line out here like that. Okay? And actually, I'm going to put the 30 degrees in there. I'll explain why I'm doing that in a moment. Okay, now here's the deal. This is the trick to doing this question. When he's in this position, so let's go back up to our picture. When the guy's right here in our system diagram, in that spot, from where he's standing, where's the center of the circle? And the answer is the center of the circle is where the rope is attached, okay, at the top. That's always true in a vertical pendulum. So the radial acceleration is going to be along that rope, okay? So that means that our y-axis, if you like, okay, like he's going to have radial acceleration that way, and that we're going to make that our y-axis. Okay, now here's the thing. He's moving that way, okay? He's moving this way, and that is perpendicular to the radial line. It's a tangential line. Okay, I know I haven't drawn it very well. So it's sort of perpendicular here. That's our x-axis, okay? And our x and y-axis have to be perpendicular, but this is the direction he's moving. Now, I know velocities, we don't usually put them on these diagrams, but he's moving that way, okay? And here's the thing, which vector is off axis? Well, if my y-axis is towards the center and my x-axis is sort of tilted like this, okay, as you see here, my x-axis, you know, like I don't want to use a little rainbow color here, maybe, like there's my x-axis. See, my x and y-axis are tilted just like they were with inclined planes, but this is very different from an inclined plane problem. But nevertheless, I actually have two accelerations on this object. So let me use the rainbow again. This guy is also going to accelerate that way, and that's the tangential acceleration. So we call the y-axis the radial axis because it's towards the center of the circle, and the x-axis is a tangential axis this time. So those are the terms that we use, but really who cares what the terms are? We're just going to solve this the way we would solve now that we've sort of picked our components. We recognize that gravity is off axis, so gravity has a component like this and a component like that, and you see why I put the 30 degrees there. Okay, that one's going to go with sine, that one's going to go with cos, and now I am ready to go. Let's do the y-axis first, and by the way, this vector, I need to draw it a little closer, that's the tension, of course. Okay, so let's do the y-axis first. Well, the tension is on axis, and I have to make the direction of the acceleration positive, of course. So that means the red vector for gravity is negative, and my tension is positive. So now I'm going to go F net equals, okay, the force of tension. Now this is in the y direction only, minus the force of gravity times the cos of 30 degrees. Okay. Now I'm going to go MAR, because this is radial, equals FT minus MG cos 30. Now here's the deal. I know what AR is because every time you do a circle, AR equals V squared over R. Well, I know what those two variables are. I know V is 3, and I know R is, I changed it to 2, right? The length of the rope is the radius of the path. So that's V squared over, that's 9 over 2. So that's 4.5 meters per second squared towards the center. And so when you look at this, I actually only have one unknown. I know the guy's mass. Guy's mass is 50, right? So this is going to be 50 times 4.5 equals the force of tension minus 50 times 9.8 times the cos of 30. There's only one unknown here, guys. Force of tension. That's one of the ones I'm looking for. So long story short, what's the force of tension in this picture? Well, it's going to be 50 times 4.5 plus 50 times 9.8 times 30 cos, right? And that's going to be 649 newtons, and man, he's going to have a hard time holding on there. Okay, that's a lot of weight, but I mean, it's less than his own weight. So, like, I mean, no, actually, it's a little bit more than his own weight. So it's more than what he would weigh if he was just trying to pull himself up on a rope. Okay, so there you go. 50 times, 649 newtons. That's how much tension is in the rope currently. Now it's going to change as he goes down. Actually, that tension is going to increase because it's going to speed up, okay, as he goes down because of gravity, right? Now that has answered, we've answered 2 of the 3 questions. We got the radial acceleration. That one's easy. It's V squared over R. We got the tension, no problem. We used a free body diagram. What about the tangential acceleration? Well, we haven't looked at the x component yet. So let's look at the x component, which is really the tangential component in this case. The x component, we only have one force, and it's the force of gravity times the sine of 30, okay? And we're going to make, sort of down and to the right positive. There's no other negative vector there. And so I'm going to go MAT, which is the tangential acceleration, equals mg sine 30. Here, we don't need the mass, and we get the tangential acceleration equals 9.8 times the sine of 30, which happens to equal 4.9 meters per second squared. No problem. Now we got our last guy there, and look how straightforward that was, okay? Now I hope, I mean, this is a video, you can rewind it and look at it again, but that is how you do vertical pendulum, okay? So there you go, vertical pendulum. Now let's do one more example. And for today, I have the conical pendulum for you. Now, the conical pendulum is another example of circular motion where it looks like this. Okay, so maybe this one won't hypnotize you. So like, the way an arm in a grandfather clock swings around, that's a vertical pendulum, okay? But this one is swinging in a horizontal circle, okay? And there are several rides, like at Canada's Wonderland, that move this way. We'll talk about those later. Pardon me, I'm getting tired. But anyway, let's look at the conical pendulum. And what we'll do is we'll sort of freeze the motion, and we'll freeze it, whoops, on one side. Okay, we'll go over here, like this. Okay, here's our object moving around in a horizontal circle. So this would be the radius. I'm going to also have it attached somewhere here at the top. We'll call this angle here, whatever. Actually, let me make sure should I do this in general terms, or should I give you a specific example? All right, I'm just going to say that that's theta, okay, for now. And I'll make this a general case. And then when you're doing the homework practice, you can see if you can apply that to a specific example, okay? So here's the deal. This time the object's tangential component will be hard for me to draw because it's actually coming towards you, okay? So in other words, the guy's moving around this horizontal circle. Let's see if I can time it. The other guy, right? He's moving around this horizontal circle. So in this position here, it's actually coming towards you, believe it or not. That's kind of the three-dimensional sense of it. And I'm trying to drop this vertical line so it goes right in there. And that's it, okay? Now, the length of the rope, we'll call that L, okay? And I just want to point something out. This right angle triangle, R will equal L sine theta, because L is the hypotenuse of this little triangle here, okay? And R is the opposite side. Okay, so I just want to point that out to you. And let's take a look at the free body diagram of this object right here. So, like, once again, it's a free body diagram thing, right? So here's how you do a conical pendulum. The free body diagram of the object in this current position, it is right now, looks like this. In fact, it looks a lot like the one we just drew. There's tension going off like this. This time theta is right there, okay? And then there's gravity that's straight down. Now the difference this time is when the object is in this position here, as I've drawn it for you, ask yourself, where's the center of the circle that it's moving in? Well, it's no longer along the rope. It's actually horizontal. So the center of the circle is over here, okay, where I've drawn the X. Here, I'll use a rainbow if it lets me. So here, let me erase this. This is where the center of the circle is. Therefore, R is along this line like this. Okay, that's where the radial line is. So therefore, this object has radial acceleration in that direction currently. Now, the tangential acceleration would be towards you, but this object is not accelerating tangentially, only radially in this case. It's keeping a constant speed as it goes around the circle, right? Now, if that's true, then our x-axis is actually going to be horizontal, and our y-axis is going to be vertical. And we can see that the off-axis vector this time is tension. And the tension has a component like this and a component like that. That one will go with sine. This one will go with cos because it's adjacent. Okay, and now let's look at our components. Okay, well here we get, let's look at the y components first. The y components, you're going to get, I'm going to say up is plus because ay is actually equal to 0. In this case, it's not accelerating up or down. So I'm going to make up plus. That means that the net vertical force will equal the force of tension times the cos of theta minus the force of gravity. This is 0 because ay is 0. So therefore, mg equals ft cos theta, right? And now let's look at the x component. So let's separate that out. Let's look at the x component. And here there's only one vector in the x direction, and it's the blue vector here that goes with sine. So therefore, I'm going to write MAR equals FT sine of theta. Now, how do we solve the system of equations? Well, what you're going to do is you're going to put v squared over r equals AR. That's our special formula for circular motion. And then you're going to divide these two equations. So if I take this equation here and go mg equals ft cos theta, well, if I just divide those two equations, the mass will cancel, the tension will cancel, and I get AR over G equals tan of theta. Okay, now we've done that trick before. We did it with the dice and the mirror and stuff. This is a very different scenario, but it still works this way. Okay. So anyway, there you have it, guys. That's how you do a conical pendulum. Now I just set it up for you. I am going to leave it to you to try to do some other examples. So now we've looked at vertical pendulum, conical pendulum. You can do a whole bunch. Before I sign off here, just let me point out, you can do a whole bunch of other questions. You can do a car driving over a bump like this, and you would get your radial acceleration that way. Okay, and if it's speeding up, that you would have your tangential acceleration this way. Okay, that could be an amusement park ride, right? Where he's going over a bump, like the behemoth does this and sends you into like this feeling of free fall. Okay, so now that I've pointed all that out to you, let me show you the work I would like you to do. I have some circular motion practice, but I don't want you to do all of it, believe it or not, okay? I want you to do some of it. So let me highlight the questions I would like you to do for now. Number 1, okay, give that a shot. Number 4, okay, I know they're not numbered right, but get over it, okay? So number 4. Now number 4, by the way, is as shown, it says. I think the numbers that are shown, oh no, yeah, it's all good. Okay, so this is based on a lab that we sometimes do. I'll show you that lab, but you can give this one a try. This is a conical pendulum, okay? All right, try number 3. The second number 3. Number 4. Don't do the banked curve yet, but you can do the conical pendulum, that number 2 down there. And that's all. I don't want you to do the other ones. I don't want you to do any orbital questions just yet. So a few questions for practice. Give those a try. They're just conical pendulum mostly, but there's also a couple of thinking questions I want you to try. But that's it, guys. Sorry, past my bedtime. But I hope you enjoyed this video, and I will talk to you soon enough. Okay, see you soon. Good night.